In the 17th century, science was changing its shape. The old world of inherited authority and unquestioned tradition was beginning to give way to observation, experiment, and proof. Knowledge was no longer accepted simply because it had been written by ancient thinkers. It had to be tested, measured, and seen. This shift would create some of the greatest scientific minds in history, and among them stood one of the most brilliant, restless, and often overlooked figures of the age, Robert Hooke. Unlike some scientists remembered for a single discovery, Hooke seemed to exist everywhere at once. He was a physicist, astronomer, architect, inventor, microscopist, surveyor, and natural philosopher. He designed instruments, improved experiments, studied the movement of planets, examined the smallest structures of life, and helped rebuild one of Europe's greatest cities after disaster. His mind moved constantly, searching for patterns in everything around him. Yet despite the scale of his contributions, his name often stands in the shadow of others. History remembers Isaac Newton with clarity. It remembers Galileo, Boyle, and Darwin. But Robert Hooke, whose influence touched nearly every branch of early modern science, is often mentioned only briefly, usually attached to one phrase, Hooke's Law. In reality, his life was far larger and far more complicated. Robert Hooke was born in 1635 on the Isle of Wight, in England. He was not born into wealth or power. His father was a clergyman, and the family lived modestly. As a child, Hooke was often sick and physically fragile, and many believed he would not live long. Because of his poor health, he spent much of his early life indoors, observing, drawing, and taking apart mechanical objects to understand how they worked. This habit of dismantling and rebuilding would define him. He showed an unusual talent for mechanics and design, able to understand complex structures through direct examination. Even as a boy, he could take apart clocks and reconstruct them, seeing systems where others saw only finished objects. After his father's death, Hooke moved to London and eventually entered Westminster School, where his intelligence quickly became clear. He later attended Oxford, a place that at the time was becoming one of the centers of the new scientific movement. There he entered a world of experiments, discussion, and invention. He worked with some of the leading thinkers of the period and became closely associated with Robert Boyle, one of the founders of modern chemistry. As Boyle's assistant, Hooke helped build the air pump used in experiments on gases and pressure. This work was crucial in the development of what became known as Boyle's Law, describing the relationship between pressure and volume in gases. While Boyle received most of the recognition, Hooke's technical skill and experimental precision were central to making the research possible. This pattern would repeat throughout his life. Hooke often stood at the center of discovery, but not always at the center of fame. His own independent work soon made his brilliance impossible to ignore. In 1662, he became curator of experiments for the newly formed Royal Society of London, one of the most important scientific institutions in Europe. This role required him to produce regular demonstrations of new experiments, often weekly, for other scholars and members. It was a demanding position, forcing constant invention and relentless curiosity. For Hooke, it was the perfect environment. He investigated springs, motion, combustion, fossils, gravity, astronomy, and light. He was not interested in staying inside one discipline. He treated nature itself as a single puzzle, with different parts connected by hidden laws. One of his greatest achievements came through a device that was still relatively new to science, the microscope. Microscopes had existed before, but Hooke transformed them into serious scientific instruments. He improved their design and used them not as curiosities, but as tools for understanding life. In 1665, he published Micrographia, one of the most extraordinary scientific books of the century. It contained detailed drawings and observations of objects seen under magnification, insects, plants, feathers, needles, and countless other structures invisible to the naked eye. For many readers, it was the first time they had seen the hidden complexity of the natural world. The book caused fascination across Europe. People were stunned by the intricate design of a flea, the terrifying detail of a louse, the geometric structure of snowflakes, and the strange beauty of ordinary objects seen up close. It was not just science, it was revelation. While examining thin slices of cork, Hooke noticed tiny box-like compartments. He called them cells because they reminded him of the small rooms used by monks in monasteries. He could not know it then, but this simple observation would become one of the foundational concepts of biology. The word cell would remain, eventually describing the basic unit of life itself. This alone would have secured his place in history. But for Hooke, it was only one part of a much larger life. He was not a man of a single discovery. He was a man driven by endless observation, a mind that refused stillness, always searching for the mechanism beneath appearance. And as London itself would soon be consumed by fire and ruin, Hooke's work would move from the invisible world under the microscope to the rebuilding of an entire city. In September 1666, London was consumed by one of the greatest disasters in its history. The Great Fire of London began in a bakery on Pudding Lane and quickly spread through the tightly packed wooden streets of the city. Strong winds carried flames from house to house, and within days, much of medieval London had been reduced to ash. Thousands of homes were destroyed, churches collapsed, businesses vanished, and the heart of the city was left in ruins. For many, it was a catastrophe. For Robert Hooke, it was also a moment where science, engineering, and practical problem-solving would be tested on the largest possible scale. Hooke was not only a scientist working in laboratories, he was also a gifted surveyor and architect with an extraordinary ability to think in terms of structure and design. His mind that examined springs and microscopes could also examine streets, foundations, and buildings. After the fire, London needed more than rebuilding. It needed reimagining. Hooke became deeply involved in that effort. Working closely with the architect Christopher Wren, he helped survey the destroyed city and plan its reconstruction. The scale of the task was enormous. Streets had to be mapped again, property boundaries re-established, and new buildings designed with safety and durability in mind. It required precision, speed, and constant negotiation. Hooke worked tirelessly. He spent years walking the damaged streets, measuring land, resolving disputes, and helping shape the physical future of London. Much of this labor was invisible compared to scientific fame, but it was essential. Without accurate surveys and practical planning, rebuilding would have collapsed into chaos. One of the most famous results of this period was the monument to the Great Fire of London. Designed by Christopher Wren and Robert Hooke together, the great stone column still stands today near the place where the fire began. It was built as both a memorial and a scientific instrument. Hooke imagined it could be used for experiments involving gravity, pendulums, and telescopic observation, showing once again how he refused to separate architecture from science. This blending of disciplines was typical of him. To Hooke, knowledge was not divided into separate rooms. The same laws that govern motion in the heavens could help design stable buildings on Earth. Science was not abstract. It was something that could rebuild cities, improve tools, and solve practical human problems. At the same time, Hooke continued his scientific investigations with extraordinary intensity. He studied mechanics and elasticity, leading to one of his most famous contributions, Hooke's law. This principle described how springs behave under force. In simple terms, it showed that the extension of a spring is proportional to the force applied to it, as long as the material remains within its elastic limit. Today it is often summarized as force equals the spring constant multiplied by displacement, but at the time, it represented something larger. It showed that nature could be described through mathematical relationships that were both elegant and predictable. Hooke expressed this idea with a Latin phrase, ut tentio sic vis. As the extension, so the force. This law became foundational in physics and engineering, influencing everything from bridge construction to mechanical design. It remains one of the clearest examples of how physical systems can be reduced to universal principles. But Hooke's interests reached even further. He studied fossils and began to challenge the common belief that they were merely strange rock formations or playful accidents of nature. He argued that fossils were the remains of once living organisms, preserved over time. This seems obvious now, but in the 17th century it was a bold claim. Even more remarkably, he suggested that some of these species might no longer exist. In other words, extinction. This was a dangerous idea because it challenged traditional assumptions about the fixed perfection of creation. If species could disappear, then nature was not static. It had a history. It changed. Hooke was beginning to see deep time before geology had fully formed as a science. He observed layers of rock and fossil distribution, suggesting that Earth itself had undergone enormous transformations. Floods, earthquakes, and gradual changes had shaped the land over long periods. He was pushing beyond simple description toward a historical understanding of nature. He also studied astronomy. Using telescopes, he observed Mars and Jupiter, mapped lunar craters, and speculated about planetary motion. He believed that planets might move according to attractive forces pulling them toward the sun, an idea that placed him close to one of the greatest scientific revolutions of the age. This would bring him into conflict with Isaac Newton. Both men were brilliant, ambitious, and deeply protective of their ideas. Hooke believed he had contributed important insights into the principles of gravity and orbital motion. Newton would later develop the full mathematical theory of universal gravitation in his Principia, becoming one of the most celebrated scientists in history. Hooke felt overlooked. He believed Newton had taken ideas he had helped shape without giving proper credit. Newton, in turn, saw Hooke as difficult, suspicious, and overly eager for recognition. Their relationship became one of the most famous rivalries in scientific history, bitter and personal, extending far beyond simple disagreement. This conflict would shape Hooke's later reputation. Newton's influence after Hooke's death was immense, and many historians believe that Hooke's legacy suffered because of it. Portraits disappeared, recognition faded, and the public memory of Hooke became strangely incomplete. But during his life, there was no question about his importance. He stood at the center of English science, rebuilding London by day and redefining natural philosophy by night. He moved between architecture and astronomy, fossils and springs, microscopes and planets, carrying the same relentless curiosity into every field. He was not simply studying the world. He was helping invent the modern way of understanding it. As Robert Hooke moved deeper into the later decades of the 17th century, his reputation as one of England's greatest scientific minds was firmly established, but so too was his reputation for conflict. He was brilliant, productive, and endlessly curious, yet he was also known for being difficult, suspicious, and deeply protective of his ideas. His life became increasingly defined by both discovery and dispute, and nowhere was this more visible than in his long and bitter rivalry with Isaac Newton. To understand this conflict, it is important to see how close their work had become. Hooke had spent years thinking about motion, gravity, and planetary orbits. He believed that celestial bodies were influenced by attractive forces and that planets moved in curved paths because of these invisible pulls. He proposed that attraction increased as objects came closer together, and discussed the possibility that planetary motion could be explained through mathematical laws. These were powerful ideas, but Hooke had not fully proven them. He often worked through intuition, observation, and conceptual insight rather than complete mathematical demonstration. Newton, by contrast, possessed extraordinary mathematical ability and was able to turn broad ideas into exact universal laws. When Newton later published Philosophiae Naturalis Principia Mathematica in 1687, he presented the law of universal gravitation with a precision that changed physics forever. Hooke believed he deserved more recognition. He argued that he had given Newton essential ideas about gravitational attraction and orbital motion before the Principia was written. Newton did acknowledge some correspondence, but he strongly resisted the suggestion that Hooke was the source of his theory. He believed the mathematics and proof were entirely his own and saw Hooke's claims as exaggerated. The dispute became deeply personal. Neither man trusted the other. Hooke felt dismissed and overshadowed. Newton felt attacked and irritated by what he saw as Hooke's constant demands for credit. Their conflict was not only about science. It was about reputation, recognition, and the fear of being forgotten. This rivalry would leave lasting consequences. Newton lived longer, gained greater public fame, and eventually became president of the Royal Society. Hooke, despite his vast contributions, would not enjoy the same lasting visibility. Later generations often remembered Newton as the giant of the age, while Hooke's name faded into partial obscurity. But Hooke's work during these years remained extraordinary. He continued his studies in astronomy, making detailed observations of celestial bodies. He carefully examined the rotation of Jupiter and the changing surface of Mars. He mapped lunar craters and used telescopic evidence to challenge older assumptions about the perfection of the heavens. The moon was not a smooth, divine sphere. It was a physical world with mountains, valleys, and scars. This way of thinking was revolutionary. Hooke treated the heavens and the earth as part of the same physical reality, governed by the same laws. He rejected the idea that celestial objects belonged to a separate perfect realm. This helped strengthen the broader scientific shift toward a universe governed by universal principles rather than divided into separate worlds. His work on timekeeping was equally important. Accurate clocks were one of the great technical challenges of the age, especially for navigation at sea. Determining longitude depended on precise time measurement, and Hooke devoted significant effort to improving spring mechanisms and watch design. He proposed the use of balanced springs in portable watches, a major step in the development of accurate personal timekeeping. Again, credit became complicated. Others, including Christian Huygens, were also working on similar ideas, and disputes over priority followed. This was another pattern in Hooke's life. He was often at the center of innovation, but recognition was frequently shared, disputed, or lost in controversy. His personality played a role. Hooke kept detailed notes of his work and constantly worried that others would take his ideas. He could be sharp in argument and relentless in defending his claims. Some colleagues admired his genius, but found him exhausting. Others saw him as too quick to accuse and too slow to let go of perceived insults. Yet beneath this difficult reputation was a man carrying enormous intellectual weight. As curator of experiments for the Royal Society, he was expected to produce demonstrations constantly, often with limited time and resources. This was not occasional work. It was a continuous demand for invention. Week after week, he had to surprise, explain, and expand the scientific imagination of his age. This pressure shaped him. It made him both astonishingly productive and deeply strained. Hooke was rarely allowed the calm space needed to build a single monumental theory like Newton's Principia. Instead, his genius was spread across hundreds of problems, each demanding attention, each adding to a legacy too broad to fit neatly into one title. He was also increasingly affected by poor health. The physical weakness that had marked his childhood never fully disappeared. Long hours, constant labor, and the stress of professional conflict wore him down. Yet he continued working with remarkable intensity, as though rest itself were a form of failure. In these later years, Hooke had become something unusual. He was both central and isolated. Everyone in English science knew his importance, yet he often felt underappreciated. He had helped define microscopy, mechanics, architecture, astronomy, and geology, yet he was still fighting for acknowledgement. He was building the foundations of modern science, while fearing that history might leave him behind. In many ways, that fear would prove justified. But before the silence of history settled around his name, Robert Hooke had already done enough to shape centuries. He had shown that truth could be found in the smallest cell, the deepest fossil, the tension of a spring, and the motion of planets. He had helped transform curiosity into method. And even as rivalry and recognition clouded his later years, the force of his mind continued pushing science forward. As Robert Hooke entered the final years of his life, the pace of his work did not truly slow, even as his body increasingly demanded it. He had spent decades living at the center of England's scientific revolution, carrying the weight of constant experimentation, endless observation, architectural labor, and intellectual conflict. By now, he was not simply a scientist among others. He had become one of the living structures of the Royal Society itself, a mind so woven into the institution that it was difficult to imagine it without him. Yet age and exhaustion were beginning to show. Hooke's health had always been fragile. He suffered from chronic pain, headaches, and physical weakness, conditions made worse by relentless overwork. He slept little, worked constantly, and seemed driven by the fear that stopping would mean disappearing. His notebooks reveal a man still recording, still calculating, still observing, even when his body was clearly failing. There was something restless about him that never left. He could not accept the world at surface level. Every object, every motion, every structure seemed to demand explanation. A spring was not just a spring. It was a law waiting to be expressed. A fossil was not just a curiosity. It was evidence of a forgotten world. A ruined city was not simply destruction. It was a problem of geometry, engineering, and human survival. This way of thinking made him brilliant, but it also made peace difficult. His rivalry with Newton remained unresolved. By the late 17th century, Newton's fame was rising rapidly, especially after the publication of the Principia. Hooke watched as Newton became the dominant intellectual figure of English science, while his own contributions were often treated as secondary or forgotten. He believed this was deeply unjust. In his mind, he had helped shape many of the ideas now associated with Newton's greatness. Whether history fully supports that claim is still debated. What is clear is that Hooke felt it intensely. Recognition mattered to him, not merely out of vanity, but because he understood how easily scientific credit could vanish. He had seen discoveries become attached to simpler narratives, and he feared becoming a footnote in a story he had helped write. This fear was not irrational. Hooke did not leave behind one single defining masterpiece in the way Newton did with the Principia. His genius was distributed across fields, spread through experiments, instruments, correspondence, observations, and practical work. He was essential everywhere, but difficult to summarize. History often prefers singular legends, and Hooke was too complex for easy legend. Still, those who worked close to science knew his value. He remained a respected and formidable figure within the Royal Society. His experimental skill was unmatched. His ability to design apparatus and solve practical scientific problems made him indispensable. Others might produce grand theories, but Hooke made knowledge physically possible. He built the instruments, tested the claims, and pushed abstract ideas into measurable reality. His work in architecture also remained visible around him. London, rebuilt after the Great Fire, stood partly as a monument to his hidden labor. Streets had been redrawn. Buildings stood where ashes had once covered ground. The monument itself rose into the city skyline, a public reminder of both destruction and reconstruction. Hooke had helped rebuild not only scientific thought, but the physical shape of the capital. In private life, however, he remained solitary. He never married and lived much of his life surrounded more by instruments than by intimacy. His notebooks suggest intelligence mixed with loneliness, ambition mixed with suspicion. He trusted observation more easily than people. There was often a distance between Hooke and those around him, as though his mind moved too quickly to fully rest inside ordinary companionship. Yet loneliness did not reduce his output. Even late in life, he continued investigating earthquakes, weather patterns, magnetism, and celestial motion. He considered whether fossils revealed extinct species, whether Earth had a deeper history than Scripture alone suggested, whether invisible forces shaped both the heavens and the ground beneath human feet. These are not small questions. They were questions about time itself, about whether nature was fixed or changing, about whether humanity lived inside a stable design or a dynamic history. Hooke was often ahead of the language needed to fully explain what he sensed. In 1703, Robert Hooke died in London. He was around 67 years old. There was no grand public monument to his scientific life. No immediate national mythology formed around his death. In fact, One of the strangest facts about Hooke is that no confirmed portrait of him survives. For a man who saw so much, history left behind almost no certain image of his own face. This absence became symbolic. It reflected how easily even immense contribution can slip into shadow when history chooses simpler heroes. Newton's legend grew larger. Hooke's became fragmented, scattered across footnotes and specialist memory. But absence is not erasure. His ideas remained. Every student learning elasticity encounters Hooke's law. Every biologist speaking of cells uses a word he introduced. Every geologist studying fossils touches questions he raised. Every microscope, every mechanical instrument, every careful experimental demonstration carries something of his spirit. He had spent his life looking deeper, refusing to accept appearance without mechanism. And though the world often remembered others more loudly, the structure of modern science still carries his fingerprints everywhere. Robert Hooke did not merely contribute to the scientific revolution. He helped build the machinery through which that revolution became possible. After Robert Hooke's death in 1703, the strange silence around his name began almost immediately. For a man who had stood at the center of English science for decades, the fading of his public memory was unusually fast. Isaac Newton, now the dominant authority within the Royal Society and already celebrated across Europe, became the defining symbol of the scientific revolution. Hooke, whose work had touched nearly every corner of that same revolution, slipped into the background. Part of this happened because Hooke's legacy was difficult to package. Newton had the Principia, a single monumental work that could stand as a monument to genius. Hooke had something less visible but equally powerful, a lifetime scattered across experiments, instruments, observations, designs, and discoveries. He was not remembered through one grand theory, but through countless foundations hidden underneath the work of others. History often rewards simplicity. It prefers the image of the solitary genius who changes everything with one perfect idea. Hooke did not fit that story. He was messy, argumentative, collaborative, suspicious, practical, and endlessly unfinished. He was the scientist of process rather than myth. He built tools, corrected errors, challenged assumptions, and opened doors that others later walked through more elegantly. Yet as centuries passed, it became impossible to ignore how much of modern science still stood on those doors he opened. His work with the microscope permanently changed biology. When Hooke looked at thin slices of cork and described the tiny chambers he called cells, he could not have imagined the scale of what that word would become. Today, cell theory stands at the center of life science. Every human body, every plant, every animal, every bacterium is understood through the concept of the cell. One observation under glass became one of the great organizing ideas of biology. His studies of elasticity became just as enduring. Hooke's law remains fundamental in physics and engineering. Bridges, machines, buildings, medical devices, and countless mechanical systems rely on the predictable relationship between force and extension that he described. It is taught so early that many students encounter it before they know the complexity of the man behind it. His geological ideas were far ahead of his time. When he argued that fossils were the remains of living organisms and suggested that some species had disappeared entirely, he was stepping toward the modern understanding of extinction and Earth history. Long before geology became a mature science, Hooke sensed that the Earth had a past far deeper and more dynamic than many of his contemporaries were willing to accept. This willingness to trust evidence over tradition defined him. He did not care whether an old belief was respected. If observation contradicted it, the belief had to be challenged. This was the true spirit of the scientific revolution, not simply discovering new facts, but changing the method by which truth itself was pursued. He also helped shape the physical world, not just the intellectual one. After the Great Fire of London, his surveying and architectural work helped rebuild one of Europe's greatest cities. Streets were remeasured. Structures were redesigned. Public monuments rose from destruction. His science was never confined to books. It stood in stone, steel, and urban form. This practical intelligence made him different from many theorists. Hooke was not satisfied with explanation alone. He wanted demonstration. He wanted mechanism. He wanted something that could be built, tested, and touched. He believed knowledge should have structure, not just elegance. In many ways, he represented the full spirit of early modern science better than almost anyone else. He crossed boundaries without hesitation. Astronomy, mechanics, architecture, biology, geology, chemistry, timekeeping, optics, they were all part of the same search. He did not believe nature was divided into separate subjects. He believed reality was one connected machine, and the scientist's task was to understand how its hidden parts move together. This vision feels remarkably modern. Today, the greatest discoveries often happen where fields overlap, where biology meets physics, where engineering meets medicine, where astronomy meets mathematics. Hooke lived this way centuries earlier. His mind refused narrow borders. Modern historians have worked to restore his place. They have re-examined his notebooks, his correspondence, and a vast spread of his work. The picture that emerges is not of a forgotten assistant standing behind greater men, but of one of the architects of scientific method itself. He was not simply present during the scientific revolution. He was one of the engines driving it. And perhaps the absence of a confirmed portrait is strangely fitting. Robert Hooke is remembered less by his face than by the way he taught others to see. He taught scientists to look closer, whether through a microscope at the hidden architecture of life or through careful experiment at the invisible laws of force and motion. He taught them that ordinary things, a spring, a flea, a fossil, a watch, could reveal extraordinary truths if examined with enough patience and precision. That may be his greatest legacy. Not one discovery, but a habit of mind, a refusal to stop at the surface, a belief that nature always contains deeper structure waiting to be uncovered. In the end, Robert Hooke was not the loudest name of his age, but he was one of its strongest foundations. Much of modern science still rests on work he began, often without realizing it. He lived in the shadow of giants, but he helped build the ground they stood on. And that is a legacy far stronger than fame.